Today we will talk about joint distributions. This will be the first video in a two-part series. Many experiments or applications require that we use more than one characteristic or variable related to the experimental units that are involved with the experiment. For example, if we are studying the body mass index of a certain population, we would need to work with at least two random variables, the height and the weight. And each of these random variables are measured in different units. If we were predicting house prices, uh, this would depend on many factors: location, house area, the number of bedrooms, the number of bathrooms, uh, and other factors. Another problem that is often of interest is to predict if the price of a stock would increase or decrease. And this depends on many performance metrics for the company involved. And in the era of social media, also on how different people tweet nowadays, right? In all of these cases, we need to calculate the probability of two or more events happening simultaneously. For example, we might want to understand the height and the weight combination resulting in a given BMI. That is, we want to work with the joint distribution of the variables of interest. We begin with the case where we're working with joint distributions for exactly two variables. In this setting, if x and y are two random variables, we would require that both x and y are discrete or both x and y are continuous. Let's work with the setting where we are working with two discrete random variables. Suppose x and y are two discrete random variables, then we know that script x is going to be the values of x and script y would be the values of y. Then the Cartesian product x cross y, which is the set of all pairs x comma y, where x belongs to script x and y belongs to y, is going to be our joint sample space for the pair of random variables x comma y. In this setting, the joint probability mass function, that is the joint PMF of the random variables x and y, is defined as the function px comma y equal to the probability that x takes the value small x and y takes the value small y. This is the probability of the intersection of two events. Note that px comma y will satisfy these two defining properties, that the probability x comma y is always going to be greater than or equal to 0, and the sum over all pairs of the function px comma y is going to equal to 1. Also, notice that if we have a subset of script x cross script y, which is an event in the joint distribution, then the probability of the event A is going to be the sum over all pairs x comma y inside A of px comma y. Furthermore, we can now talk about the marginal and the conditional distributions. The marginal probability mass function for the random variable x is going to be derived from the joint probability distribution. For a fixed value of x inside script x, the marginal is defined as the sum over all y of px comma y. Similarly, the marginal probability mass function for the random variable y is defined using the joint probability distribution as the sum of all px comma y, where x varies over the values of x and y is fixed. A third distribution is the conditional distribution associated to x comma y. The first one would be the probability of x given y. This is the probability that the random variable takes the value x, given that the random variable y takes the value y. This conditional distribution is defined as the probability of px comma y divided by pyy. Similarly, we can define the probability of p y given x as the probability of p x comma y divided by px of x. This leads us to a very important identity, which says that the joint probability distribution px comma y is going to equal to the conditional distribution times the marginal. And these are the formulae. We next talk about two continuous random variables and joint distributions associated to them. Let x and y be two continuous random variables. In this setting, the joint sample space is going to be defined as the Cartesian product of the set of real numbers with itself. So that is R2. The joint probability density function, or the joint PDF for the random variables x and y, is now going to be defined as the function f that goes from r cross r to r, and the function satisfies the following two properties: that fx comma y is always greater than equal to 0, and that the integral over the entire real plane fx comma y equals 1. Note that if we have any event inside the joint sample space that is R2, the probability that the random variable x comma y lies inside the event A is going to be equal to the area over A of the density function fx comma y. If A were a rectangle, that is a closed interval a comma b cross the closed interval c comma d, then the probability that the random variable x lies between a and b and the random variable y lies between c and d is exactly going to be the double integral of fx comma y over the closed rectangle A. Talking about marginals and conditional distributions in the context of continuous random variables, the marginal probability density function for x is defined as f sub xx, and this is the integral from minus infinity to plus infinity of the density fx comma y with respect to dy. Similarly, the marginal probability density function for y is defined as the function f sub y, and this is the integral from minus infinity to plus infinity of the density with respect to dx, and this is defined for all values of y inside the real line. Moving on to conditional probability distributions in the context of continuous random variables. The conditional density function of y, given that x takes the value small x, will have the probability density function given by f sub y given x, and it equals the joint probability density function divided by the marginal with respect to x evaluated at x. Similarly, the conditional density function of x, given that y equals small y, is going to be defined as the joint density function fx comma y divided by the marginal with respect to y evaluated at y, and this is defined for all values of x inside the real line. An important identity in this context is that the joint density fx comma y is going to equal the conditional density function times the marginals, and the formulas are as follows. We wrap up this video by talking about the independence of random variables. We say that two random variables x and y are independent if the joint PMF px comma y equals the product of the marginal PMFs for all values of x comma y if x and y are discrete random variables, or if the joint PDF equals the product of uh, the marginal PDFs for all x comma y inside R cross R, if x and y are continuous random variables. If the conditions for independence are not satisfied, we will say that the random variables x and y are dependent. Note that when the random variables x and y are independent, we can calculate the joint PMF or joint PDF by just multiplying out the PDFs of x and y. However, in general, it is quite difficult to calculate the joint PDF or the PMF of a pair of random variables. To summarize today's video, we have introduced the idea of joint distributions when we're working with a pair of discrete distributions or a pair of continuous random variables. We have then spoken about the marginals and the conditional probability distributions, and finally introduced the idea of independence of two random variables. We will be using these ideas a lot in future videos, but this is all for now. You take care of yourselves, and I will see you around.